Awesome. On that note, Mark Randel.
All right, thank you. Quick rubber duck story. I throw a party every summer and I have a theme. Last summer I did rubber ducks as a theme because I did not get my rubber ducks in the mail for Christmas, so I held a resentment. And a friend of mine brought 200 little tiny rubber ducks and passed them out to all the guests and said, hide them. I'm still finding rubber ducks in my house. The other day I had to go out and do something with tools, and inside my 5/8 socket, sure enough, a little rubber duck. Okay, so I'm going to try and get through this as relatively quick as I can because there is a musical number at the end with post-credit scenes. I like comics, so let's go with the MCU theory. So, I am Mark Randel. I'm a senior software engineer at JKI. I've been programming in LabVIEW for over 30 years. Back in 1990, I had my first taste of it with version 2, and I haven't looked back since. I've been in pretty much most industries. Most recently, before joining JKI, I was at SpaceX for over 6 years. And that's a good reason to have this as my giants are female, because Gwen Shotwell is awesome. A lot of people think Elon runs SpaceX, and that's sort of a misnomer. He just messes with the engineering teams all the time. That's his job. Gwen is the one that actually runs the company. Her office was actually right near mine in the McGregor office, and so every morning I would say good morning to her, and she was just very inspirational, just a fantastic coworker. So, before making this presentation, I thought it'd be a good idea to look up the definition of determinism. Evidently, it's a philosophical definition too, and I had to really dig hard to find the proper programming method or programming definition for this. So it is a system where future states are predictably determined by current conditions with no randomness involved. So what we're trying to do in making a deterministic system is remove all random timing. Now, Windows, as we all know and love, is just chock-a-block full of random timing with background processes and system management. Even RT, which is a very stable system, it can be vulnerable to non-deterministic behavior if you're having to reallocate memory in your process. So in here, let's look at this. This is sort of an example control system where we have a sequence of steps that we step through and just continually run. We'll just say, for instance, to make the timing systems work, we're running it at 200 hertz. So in an ideal world, we have a 5 millisecond timing delta time. And so what we would love to see is where all those delta times in all the different frames are safely well underneath that. But in reality, we end up with all these spikes and stuff. And I remember a couple years back looking at this thinking, software, it's doing the same thing every cycle. Why is it randomly, sometimes longer, sometimes shorter? And that started me down this path. And I'm not sure if that was a good thing or not, because it sort of made me a little sketchy. So, what are memory allocations? Because it turns out that that is probably going to be your biggest culprit in causing random timing behavior in your control loops. The definition is it's an assignment of physical or virtual memory for program use. Now, LabVIEW, when he first starts up, he's going to reserve a certain amount of memory. It's going to look through the software and say, okay, pretty much this is where I should expect to use stuff, and it's going to allocate as much as it can. However, while it's running, if you have something that changes at runtime, it's going to have to reallocate that memory. Things that can change during runtime, as we've already seen in the first presentation, which did throw me for a little bit of a loop this morning because I had to go back and re-verify that my test software was indeed correct. But if you have a change in array size or string sizes, and if you really want to be cruel to yourself, have an array of strings where they're all changing. So the impact on determinism is every time you change an array size dynamically while running, it has to go off to the memory manager and ask for a change in size, either more or less memory. When it's doing that, it has to wait in line if there's somebody else trying to do it, or within LabVIEW, or even in a Windows system. So it produces your unpredictable behavior in non-determinism. To be able to look into this, I started using the Desktop Execution Trace Toolkit. This thing's been around for donkey's years. And it's still a very reliable method for looking underneath the hood to see what's actually happening within your software. This presentation is not going to be a tutorial on how to use DETT. That would be a whole day-long seminar. What I am going to do is just show you some outputs from it that are solely looking at the memory allocations. So here's a good example of what we're going to be looking at. You can see in this block diagram, I create a 10-member array of doubles, and that little VI right there, that's part of DETT, where you can set a little identifier, and so you can find what you're looking for in the code. And so that's our loop start. And all this loop is doing is it's just peeling off one element at a time. And you can see each double is changing that array size. It's reducing it by 8 bytes, and then the last one is 12 bytes. So that's 8 bytes plus the 4-byte header of the array definition. So enough of all this setup. Let's apply this to a real-world situation. So in that block diagram I showed you before, we were having to spit the data out on a network. Well, this is the situation I came across, and what I'm presenting here is a really vague version of it. But say we have a huge array of our data, and it has to be serialized and spit out the door. But we can only spit it out in packet sizes. So you're going to be splitting up your array into chunks. Invariably, when you do that, that's going to be a partial size chunk. And so this is a common issue when you're sending out a lot of data over the network. So here's how I'm going to analyze it. This lab situation here is something I got from Stephen Loftus-Mercer. And it's basically a setup that allows you to, over here, you create your data object, and that's just a simple data. Right in the center is your unit under test. That is just the snippet of code. And so you feed it, and whether it has a class input or a cluster input, you plug it into this template, and so you take a timestamp right before and right after. And we've also got some of the other VIs there so that we can find it easily in the trace. And then I randomize the data every cycle, and then it's important to feed the data to the front panel, even if the data is not being shown on the front panel, because otherwise the compiler says, you're never using this, and it's going to be wonderful. So, and then by setting it up like this, we can run it tons of times to be able to get a good sample size. And of course, we all know LabVIEW runs really fast, so it shouldn't be an issue. Pardon?
Can you explain this timer with 0 seconds?
Oh, the timeout? Yeah, this is part. Yes, the 0. Yes, that is just, by doing that right before we execute the code, that actually creates just a yield to the OS. And so if the OS is having to do something, it will execute at that point, so it's not going to execute during our code, hopefully. It's sort of it's an insurance measure. It's not absolutely perfect, but it's just a little assistance to help with that.
Does it need to be like a 1? Why is it that 0?
Is that like a no-op?
It's a no-op, which functions as a yield. Because if you do 1, then it takes a little longer.
They were just checking if 0
Yes.
but that no-op answers it.
And in later templates, I actually add a no-op on both sides of it, just to make sure that we're always clear, when we're actually running the code. By the way, all of my code is, I put a link in the Discord to my GitHub where all this is located. So I actually have the code for this there plus the presentation. And it's on the Discord for my presentation. So to test this for memory allocations, I am going to create 12,000 channels, and we're going to declare a packet size of 5,000. I like nice round numbers. It's going to be easier to analyze and see what's happening underneath the hood. So what we're going to have is we're going to have 2 packets of 5,000 channels and then that one off packet of 2,000 channels. So if we start diving in, oops, don't give it away. There we go. Okay, in a traditional basic approach, and this is where I sort of panicked having seen you doing a split array, and all of a sudden, it's like, ooh, we're not doing, it's using the same pointer. Right while you were doing your presentation, I retooled this on my system, and it gets the exact same memory allocations when it's executing. You can see what's happening here is to serialize the data, we are splitting off a chunk, a subarray of, actually this would not be a subarray, this would be a new array each time, because we are taking I don't know. I'd have to play with that. But we're serializing it and then just sending it into an encoded receiver in the object. And you'll see what we do get a memory allocation. It will be happy with those 2 5,000s, but the 2 5,000s, but that one 2,000 array, it's having to make an adjustment of 3,000 bytes. That's that 2,400 for the string, and then another 24,064. That's for the array plus its headers. And so each time it's cycling through, it's having to do that. So what if we pre-allocate everything and we just take it straight through a for loop? How many of you guys use IPEs? About half. Okay, cool. IPEs, once I discovered how to use them, I love them. But they are very dangerous because as soon as you wrap your code in an IPE, you're telling the LabVIEW compiler, hold my beer, I got this. And it's going to ignore everything inside there. So you better know what you're doing when you go into an IPE. So in this case, I have everything pre-allocated, and I'm going through the for loop. I'm just IPEing the snot out of all this code, and I've got it all optimized, but look right here, I still have that memory allocation. That's annoying. That is very annoying. So how can we get around that? This is where the magic happens. I add a single case structure. And the code inside the case structure is the exact same. But all I'm doing is I'm providing to LabVIEW saying, in this set, which is the last set, it's going to be a different case. And so when it compiles, it knows on that last set, he's got his own memory space. We never actually change memory sizes. And a memory resize of 0 is as good as you can get. Now the best is just you don't see any allocations whatsoever. But a memory resize of 0 protects you, and it's never actually hitting the allocator. So a good friend of mine, Hunter Smith, I heard him in the back of my head after I went to all these great lengths putting together the presentation. And I could hear him say, yeah, but what happens if you do the extra case but without all the IPEs and stuff? What would you get then? Well, in LabVIEW 2015, I got all the memory allocations. This is in LabVIEW 2024. Damn it. What did I learn from this little experiment? The compiler improves. The compiler changes. So what was gospel 2-3 years ago, today, you don't know. So, and it's really fun because throughout all my years in LabVIEW, I'll hear so many people say, oh, you got to do it this way. Why? Well, because that's the best way. Why? Show me. Show me. This lab setup, I can't tell you how many times I've pulled snippets of code out, thrown it in, and said, "You're a liar." Or other times, it's like, "Well, I'll be. Look at that." You never know. So anytime I'm in doubt of anything, I'll throw it into the lab and I'll check it.
And that's why it's good to document.
Yes,
On the previous one, you document, I'm doing this because I'm saving X.
absolutely.
Then somebody can come back and verify if that's still the case.
Absolutely. And you can maybe even have an appointment with yourself in a year to go back and check that.
You were paying attention.
Yes, I was. All right, so now we're going to use that, because we have the delta T's in that lab, we're going to do the same thing, except now we're going to measure the performance of what the difference in timing is. To do that, I'm going to up the channel size quite a bit. I'll leave the packet at 5,000, but by having more packets or more channels, that's going to leave us 8 packets of a full size plus that off-size 9th packet. And let's see how this ends up looking. So here's our baseline. Here's the same code. We just stepped through those 4 instances. And so we have on our base code, we've got a mean average time of 220 microseconds. And that's serializing 43,000 chunks of data. I love it. One of the more important numbers to look at is that minimum time, because what is in the actual, if you're looking at the chart, you're seeing all kinds of noise, but you really want to know what's the minimum amount of time it's going to take to execute that. So that's 203 microseconds to execute. Now, when we do pre-allocation with IPEs, that is a significant improvement on time. And if you look at the standard deviation, we're not getting nearly as much variation. And in other words, that's a direct correlation with jitter. So the lower your standard deviation, the less jitter you can expect. So now let's go to the golden standard, the golden boy. Yes, look at that. Standard deviation dropped even more. Our baseline dropped even more. And it does pay off to add that little extra case. Now what you're not seeing here is this is just isolating that chunk of code. Imagine that chunk of code is running as a daemon parallel to the rest of your data, or to the rest of your process, and as a result, your process is not experiencing all those memory allocations, and it gets a lot smoother as a result. And then, of course, yeah, that stepchild, which is pretty darn good, you know, well, whatever. I still want to stick with my IPEs. It's pretty. So what have I learned from doing these labs? One is when you're doing a performance test, turn off DETT. Don't leave your DETT trace running. It does all kinds of funky things to your performance. Also, close all your other sub-VIs. Get those out of the way, because it's going to want to update the front panels. Who knows what that'll do. Don't use debugging. Make sure all your probes are off. Basically, just have that one front panel open. Also, if you can't, close out of all of your other programs. Shut down services you don't need if you really want to get picky about it. And the critical one is run all your tests at once. The first time I prepared this presentation, I had those first 3 sets of data, and it was beautiful, it was perfect, and I was on the plane when all of a sudden Hunter was bugging me in the back of my head, and I realized, oh, damn it, I'm going to have to add that 4th step, or the 4th test. So I did it, and I did it on the plane, and the performance was completely out of family with everything else. And I thought, oh, hell, there went any kind of validation I've got. So I had to rerun all my validation at that point on my laptop on battery power, not plugged in. The time of day even can have an effect. Who knows? You know, always run all your performance tests at the same time under the exact same situations.
Sometimes I find you just have to close LabVIEW and open it because somehow everything got slower.
True, yeah, and there is that case also. And then lastly is don't rely on the performance test, because your best golden rule is how it gives you a guide on expected performance, but ultimately how does it perform in your overall system. That's your golden rule. Yes, Fabia?
Two things. One was what we said of not closing LabVIEW or running the BIs programmatically, so you're not introducing the panel being the front panel being open. When running that, it can introduce things. And also on the do not leave the Desktop Execution Trace Toolkit running. Have you tried remote running? So here's, I mean, normally when I'm using Desktop Execution Trace Toolkit is because I'm running as a firefighter. So this is like a really weird case. The extreme setup I have used for is having a computer with Desktop Execution Trace Toolkit, a computer running the code, and another computer connecting LabVIEW with the executable operating so you can see the block diagrams. So it's you never have to do firefighting. But using Desktop Execution Trace Toolkit in a different computer, you are using the network, but you remove all the space and access to disk to write to the file and everything else the Desktop Execution Trace Toolkit does.
Okay.
So you can use it as a spy in a different computer.
That's crazy. I need to try that.
I'm not sure if this is correct, but it's not only leaving that running, but leaving that open. I don't know why I found some randomness by leaving that open because it does, I don't know what it's doing.
Really?
Found that when I do the benchmark, I need to close not only that, but close LabVIEW and open LabVIEW again without that running ever.
Possibly because DETT is actually examining, you have to specify which port you're communicating on, and now you have to recycle the port once every now and then to check what it's available. DETT just might be hanging out on the same port as LabVIEW, and
Yeah.
who knows?
So when I do benchmarkings for long run tests, for example, I use that a lot for the checking stuff, firefighting. But I close LabVIEw, I close that.
Okay.
Restart the computer and then I start.
Oh,
again,
you
and then-
restart, yeah.
Yeah, I mean, yeah, I'm superstitious, right? But
Cool. Okay. So, what we've seen is that memory allocations, it definitely has an impact on your determinism. In-place elements, really need to be careful when you use them, know what you're doing, and the fun part is attempting to predict the LabVIEW compiler is a pain in the butt, especially because every new release, it's improved a little bit here or there, and when in doubt, lab it out. And I've always loved this one. And now for the big musical number. And come on.
Allocate, don't replicate, alleviate the logic gate. Draw your fate, don't conjugate. Get LabVIEW before it's too late. Times change, compilers change, methods change, lab it out. Properties change, people change, computers change, lab it out. LabVIEW. I can finally assume, but don't wanna determine determinism. Just like an exorcism, ain't no colloquialism. Cut out the masochism, your LabVIEW, get past cynicism. But don't want to change, compilers change, methods change, lab it out. Properties change, people change, computers change, lab it out. LabVIEW, I can finally zoom, but don't wanna. Finally zoom, but don't wanna. Determinism, just like an exorcism. Ain't no colloquialism. Cut out the masochism, get LabVIEW, get past cynicism. But don't want to change, compilers change, methods change, lab it out. Properties change, people change, computers change, lab it out. LabVIEW, I can finally zoom, but don't wanna, don't wanna, don't wanna. Totally zoom, but don't wanna, don't wanna. Jitter, gone.
Thank you. And that's my post-credit teaser for episodes still to come.
Which AI tool did you use for the song?
Oh, which one's, just one of them out there. But yeah, obviously I came up with the lyrics. All right, thank you.
Are there any questions from anyone? Yep.
Just one point with regard to the in-place element structure. When you optimize code and you benchmark it, the context in which you're benchmarking can be important sometimes, because the optimizations the compiler performs depends on the complexity of the code. So if you have specifically inline VIs because you're trying to optimize performance and you have that in multiple levels of, the compiler might stop performing that optimization. And so we tend to just use the IPE to make sure that it's being done properly.
Yeah, I didn't mention that with this lab. If you go inline with your VIs, all of a sudden it just disappears and it becomes part of the parent VI. So it's important not to inline your code if you want to be able to find exactly where the problems are. However, inlining does improve performance. That's a whole nother topic for another day.
One thing to, maybe two, maybe the first one's probably most important, is the LabVIEW options. Maybe people know, maybe people don't, but there's a slider in them, and there are options out there. Limit compiler optimizations or don't limit compiler optimizations. And if you're not thinking about it, right, one is supposed to speed up your IDE, right? Limit optimizations, I think, is all the way, it's weird logic. You got to read it twice to get it straight in your head, right? But of course, if you're doing this, right, if you want to speed up the IDE and the responsiveness, great. But I think that's the idea of, if you're going into this mode, flip your brain, right? Make sure that, well, one, make sure that you're looking at the options to see where it's set. And then move it to where you want it to be for your end application or the true performance. And then also you have to force recompile, I would only imagine. I guess the LabVIEW team here could confirm or deny. And then run that. Well, not only that, but probably set it, close LabVIEW, open it up, force the compile, save, close LabVIEW, open it up, and then of course lab it out, as you say.
Yes.
So I would imagine that's probably a pretty good functional model, but remembering that slider there is probably pretty key.
Right, everything that I did here was just done with the default settings on that slider. I did not alter any of the optimization.
Well, do you find that you do that as well? I mean, obviously for the presentation's one thing, but do you actually move it around when you're in development mode versus I want to actually eke out my compiler performance?
I've learned not to. I tend to leave that alone. Same way as changing the LabVIEW or the VI priorities on execution priorities. That's a slippery slope that when you start messing around with those, because they get inherited easily, you can end up bogarting processing time on something that's not even necessarily needs it because it inherited from the parent.
I'm with you on that. I don't know if lumping those two things together as kindred spirits of problems are fair, but
yeah, that actually is a really good point, though. So sounds like my next lab that I'm going to need to experiment and present on.
Thank you. Great presentation.
Thanks. Any other questions? All right. I think it's break time.